have on the Manassa. It doesn't matter. Today's lecture, we're going to continue with what we talked about last time. If you just recall, last lecture we began talking about operations on a single random variable, where we talked about expectation. This is the first operation, chapter 3, and as you can see on the screen right here. And also we had a few examples on that. And the last page of last lecture, we talked about expected values of functions of random variable, where we took the expected value of a function rather than just the random variable itself, a function of the random variable, which is equation 9, and this is for the discrete random variable. So today we're going to build on this. So we're going to use this equation 9 and equation 10, okay, to talk about moments. Okay, so moments is an application of the expected value of a function g of x of random variable. So, like I said, so this is the, we replace, if you go back to equation 1 here, we replace x with its function, with the function of x, okay? And now here, we're gonna call it the moment, okay? So basically the moment is the expected value of a function of random variable, okay? Now we have two types of moments, with the moments of about the origin and moment about the mean. So we're going to begin with the moment about the origin, okay? Which is, this is the nth moment of the random variable x is defined as the expected value of x to the power n, where x to the power n is the function of x, okay? Which is the same equation on here, page 50 of last lecture, okay? Now, the same thing as far as the discrete random variable, the only thing we did, we just replaced g of x with x subscript I to the power n, okay? Now we have, of course, you know, the nth moment. So we have the first moment, second moment, third moment, depending on the application you are looking for. Now for the 0th moment, okay, which means if n is equal 0 in here, equation 1, we will end up with what? We're going to end up with the integration of the PDF. And of course, this is the area under the PDF. And if you recall, the property of the PDF, the area under the PDF is equal to 1. And of course, when you do the integration for the PDF, will have to be equal to 1. Now, the first moment is basically the mean, which is the expected value, because all you have to do is replace n with 1. So that will go back to the original expected value, okay? Now, this is just a simple example here. So if we are given this PDF, equation 3, it's a uniform PDF for random, a uniform random variable, okay? 1 over a, where the random variable x between 0 and a. Now we need to find the first moment and the second moment. And this is very straightforward. All you have to do is just plug it back into this equation right here, equation 1. Of course, the first moment, n will be 1, and the second moment, n will be 2. And you just do the math right here. You know, simple integration. Of course, the integration limits will be between 0 and a, because it's already given to us in the PDF, okay? And this is the second moment. So the first moment is a over a2, and the second moment will be a squared divided by a, and you integrate from 0 to a. And when you do the integration, will be x3 to the power, or x to the power 3 divided by 3a. A squared divided by 3 after you do the math, okay? So this is very, you know, nothing new. The only thing we just, you know, introduce a new topic, which is the moments, which is obviously related to what we talked about last time. Okay. On page 52, This is the same example. We've done this a couple of times for discrete random variable. We need to find the third moment. Of course, as you can see here, random variable has 4 values or 5 values rather, and the PMF for each value is given to you. We need to find the third moment. Of course, we go back and use equation 2 right here. So 1 by 1, and you sum them up like we did before, nothing new. Of course, this is the PMF, for example, the first one is 0.35 for the value 1. So it will be 1 to the power 3. The second one, 0.2 or 0.1 rather, times 2 to the power 3, and so on. And that will be the third moment. So you can find the first moment. We did find the first moment, which is the expected value. Okay. So this is what we call the moments about the origin. Now let's talk about the second type, which is central moments. Now, central moments, a moment about the mean value of a random variable is called central moment. So it's central moment, and we're gonna, it's basically, as shown in equation 6, it's the same as the origin, okay, the same as equation 1. The only difference is we are shifting the random variable by the mean, okay? So instead of x to the power n, that would be x minus mu of x, which is the mean, okay? So the origin now, in the first one, mu was 0, where this one here, mu is a number, okay, constant, of course. So it'll be x minus mu x to the power n. And, you know, you do the same thing. That's the difference, okay? So our function here, instead of being x squared or x to the power n, the g of x in this case would be x minus mu of x to the power n. And you do the integration like we did before, okay? And of course, we refer to this the central moment, or the nth central moment, mu of n, okay? So it could be mu1, mu2, mu3, whatever, okay? And the same thing as far as the discrete. So we replace xi to the power n by xi minus mu of x to the power n, okay? Now, the second central moment, mu subscript 2, we're going to refer to it as the variance, okay? And we're going to refer to it, the notation for it will be sigma squared, or sigma of x squared. We talked about variance before, if you remember, when we talked about Gaussian, okay? Now we're going to talk about it in terms of central moment, okay? Now the variance, obviously, it's equal to the expected value of x minus mu of x to the power 2, because it's mu2, where n is equal to. Now, if you go back to last lecture, last page of last lecture, and use this identity, equation 11, where we said the expected value of a of x plus b is equal a expected value of x plus b, and use this identity to break this equation right here, inside the brackets right here. So this one here, x minus mu of x squared is equal to the expected value of x squared minus 2x mu of x plus mu x squared, okay? So these are equal. Now, according to the identity I just shared with you from last lecture, طبعا هنا mu of x is constant, okay? So we can take it out. So this here, this equation can be broken into the expected value of x squared minus 2 mu of x constant times e of x plus what? Plus the expected value squared, because this one is out, it's constant. All right. Now, of course, the expected value, e of x, it's the expected value. So we have mu of x times mu of x will be 2 UMX squares. Then after you do the math here, you will end up with equation 8, which means the variance, sigma squared, is equal to the second moment of the random variable x minus the mean squared of the random variable x. That's what we are looking for. So in order for us to find the variance for a random variable, you need to find the second moment for it, and then you find the mean for it, and you square it, and use this identity right here. And of course, the standard deviation, as we learned before, is the square root of the variance. Any questions so far? Okay, it's very straightforward, nothing new really. Okay, now let's go to page 53. Let's use the same example, the discrete random variable. Again, we just used it a minute ago, where we have the values of the discrete random variable and the PMFs. Okay, now we go back and use this equation 7. Now, what we need to find the variance and the standard deviation. The variance, like I just said, we need to find the second moment and the mean. Now, the second moment, we all know how to do it. Like, you take the first one, 0.35 times 1 squared plus 0.1 times 2 squared, and so on and so forth, would be 37.15. And the mean, we did find it last lecture. It's 4.75. You can go back to the notes for last lecture and you verify that. Now, since you have this information, you have the second moment and the mean, you just go back to this equation 8, and plug in the numbers, and you will see that the variance is equal to 14.5875, equation 10. And from there, we can find the standard deviation by taking the square root of this value right here, 14.575, which will end up with almost 3.819. Okay. In here, we have two inequalities. I'm not going to go through a lot of details as far as these inequalities. Just these are, they are popular. Will be nice to, at least will be to be introduced to you. Okay, I'm not going to go through a lot of proofs. The proofs are in the book, and you can prove them easily. Okay, but what we are interested in, just the equation. So we have the first one. It's called the Markov's inequality. Of course, these inequalities, they are, again, we use them for some analysis later on, maybe, especially in communication, and maybe, some other applications as well. They will help you to analyze a network or a mathematical equation, will make it easier to deal with, all these inequalities or, identities. So in this case here, let's say we have a random variable x is a non-negative random variable, okay? Then the probability of the random variable x larger or equal to a, where a is larger than 0, this probability is less or equal to the expected value of x divided by a. So if you need to find what's the probability of x larger or equal to a, first of all, you need to find the expected value and divide it by a. So that's the identity we are interested in. Now, as far as the proof, like I said, it's in the book. What you can do, you can begin with the expected value here, and of course, the expected value, it's equal to the integration of x. The integration of x times the PDF of x from 0 to infinity, since it's non-negative, okay? And from there, you continue with that, and you will end up with proving this one. It's proving the proof for this one. It's it's in the book, but this is what we're interested in. We're not really interested in the proof. And another identity, another important one, or it's well known. It's called the Chebyshev Equality. Okay, this deals with variance. Okay, so let's assume that x be a random variable with the mean m and variance sigma squared. Okay, so what's the probability that x takes on a value that's removed from the mean by more than a? Now it says removed by the mean, so the shift can be from to the right or to the left. So this probability is going to be the probability of the absolute value of x minus m, because the shift will be to the right or to the left. It's larger or equal to a. Okay, so what's this probability? This probability is equal to it's less than or equal to sigma squared. Now the variance of x, okay, you need to find this, the variance of x divided by a squared. Okay, again, the proof, it's in the book, and it's related to the first one as well. Okay, and that's all I have for today. Okay, like I said, hopefully next week we will finish chapter 3. Okay, and the week after, of course, maybe we will have a lecture before the exam or so. We'll begin with chapter 4, but I'm not going to include chapter 4 in the exam. Okay. Any question related to today's topic, to the notes? Okay. Okay. If you don't have any questions, I will talk to you inshallah next Sunday. يعطيكم ألف عافية.
الله يعافيك.
يلا،